Welcome back everyone to the Linear Regression Project Solutions lecture. In this lecture, we're going to go through the project and show an example solution set. Keep in mind, I highly encourage you to check out other models and see if you can improve on our own results shown here. Let's jump to the notebook and get started. Alright, here I am at the project exercise notebook. Let's go ahead and run the imports and read in that final data frame. Okay, so here we have this very large data frame. Recall, we created many features, but what's really nice is later on, we'll use the elastic net regularization method, which also incorporates lasso, which means we should check the coefficients of that model to discuss which features are actually important and which are not. Right now, this is a very feature-heavy data set, and we may want to consider just including a few features from this. But let's go ahead and continue and see what we can do. So we can see the data frame. We can see 𝑑𝒓_info has about 3,000 rows and these 274 columns. What we're going to do now is do the first task. Recall that the label we're trying to predict is the sale price column. So this is really easy to do as far as separating out features. And we can do this mainly because of the kind of almost 1 or 2 hours of work we did earlier in the previous section to clean this all up. So I'm going to say x is equal to 𝑑𝒓_drop along axis is equal to 1. And then I'm also going to assign my label. And the label is just equal to y is equal to 𝑑𝒓 sale price column. There we go. So I have all my features and my label, and the reason I know I can just do a simple x is equal to 𝑑𝒓_drop sale price, recall, is because of all the work I made sure that there's no missing data, and all the data that is categorical has already been cleaned up. Typically on a real-world data set, you can't just jump to x is equal to drop the label column. We did a lot of work in order to get to this one line. Now what we're going to do next is use scikit-learn to split up x and y into a training set and a test set. To do this, we'll say from sklearn.modelSelection, and then we're going to import the train test split. Go ahead and do what we always do, train test split, shift enter, and make sure we grab this example. Okay, and in order to match the solutions notebook, what I'm going to do here is I'm going to say the test size is smaller, 0.1, and the reason for that is because we're going to cross-validate across the entire training set, and so this 10% is really just my holdout set, and then we'll set random state to 101. This is just to make sure everything matches the solution notebook. Really, it's up to you what you provide for these values. Okay, next, the dataset feature has a variety of scales and units, which means we should use some sort of standard scaling. We already know how to do this from many previous examples, where we're going to say from sklearn preprocessing, import standard scalar, and of course you should carefully know what to use for fit versus what to use for transform. So after we create a scalar object saying standard scalar, we should only first be fitting and transforming to xtrain. Different ways we can do this, but what I could say is, just to make it obvious, I'm going to say scaled xtrain is equal to scalar.fit underscore transform on xtrain. That's one way I could do it. It's essentially doing two things at once. Or what I could also do, in parentheses, is call scalar fit on xtrain, and then later on, in the next line, call scalar transform xtrain, and then get the results here of like scaled xtrain is equal to this line right here. So technically this line and this line, these two lines, are the same thing as doing this all in one line. But again, notice what I'm doing here as I'm only fitting on xtrain. All the previous examples, we've kind of separated this out into two steps, but you can do it in one step to save yourself a little bit of typing. And then we also have to do it for scaled xtest. We will say scalar. In this case, we just do transform. I don't want to fit to anything in the test set, otherwise I have data leakage. And then we'll say xtest. Okay, now it's time to use an elastic net model. I'm going to create an instance of that default elastic net model. The reason I'm using default here is because later on we're going to use this grid search CV object. So this is pretty easy. What I'm going to say is from sklearn.linearModel import elastic net. And you'll notice that there was an elastic net CV, but I'm going to go ahead and just use elastic net default. That way I can have all my parameters and all the error metrics I want with grid search CV, which is the more customized way to do this. And then we say base elastic model is equal to elastic net. Then we're going to set up a parameter grid. Keep in mind you can kind of do whatever you want here as far as the choices. So I'm just going to say parameter grid is equal to, in this case we'll say alpha, and let's have a line of results here, 0.1, 1, 5, 10, and let's go all the way then to 100. And then we're going to have an L1 ratio, colon, let's go 0.1, then let's say 0.7, 0.99, and 1. Okay, so this is not the full parameter grid that's shown in the solutions, but the more parameters you add in, the longer it's going to take. So just keep that in mind. Okay, so there's our parameter grid. Now it's time for the grid search. We'll say from scikit-learn.modelSelection, import grid search CV, and then we're going to say grid model is equal to grid search CV, and this is where we pass in our base elastic model as our estimator. We pass in our parameter grid as our param grid, so I'm going to say param grid here, and then we're also going to pass in the scoring metrics we want to consider. So in this case, I'm going to say this is a consideration for negative mean squared error. And then I'm going to say CV is equal to, let's just make it a 5-fold CV, nothing too crazy. Verbose is equal to 1. So we'll run that, and now we're ready to fit to the scaled version of our data. So I'm going to say grid model, fit this to scaled xtrain with ytrain. So if you run this, as I mentioned, you may get some warnings that actually happen depending on the tolerance you set. So if you're curious on how to avoid these warnings and kind of fix them in the future, they're only happening, whoops, scroll back up here, they're only happening for certain combinations of these particular alpha values and this L1 ratio value. What you can do is come back to your base elastic model and recall that we have these max iterations we can do, and we've actually edited this before. So I can say max iterations and just give it more time to kind of find the max iterations in its solver on that gradient descent. And then what you could do is just run this again. And if you run that again and fit, you shouldn't see that many warnings as long as you made the max iterations long enough. So you notice here, it's basically just fitting. And you don't get that many messages as well if you just say verbose is equal to 1. So you can always increase how verbose something is in case you want to see where it's at in its fitting. So if you have a really large set of hyperparameters, I actually would encourage you to make verbose higher, just because that way, in case you walk away and come back, you'll be able to see where you actually are in the process. So the next step is to display the best combination of parameters for our model. I'm going to fast forward in time until this is done running. All right, so that has now finished running. It took 3.1 minutes. Let's go ahead and check the results. To get the best parameters for this particular fit, all we need to do is call grid model best params. So we're going to say grid model, whoops, make sure we spell that right, grid model, and then say best params. Run that, and you can see that it looks like it wants an L1 ratio all the way to 1, and in this case it favors the particular alpha value of 100. So there's a couple things to note here. Clearly, it's going to want L1 regularization. Does that make sense? I would think so, given how many parameters we're actually providing. It's such a large feature set, it probably makes sense to just push some of them to 0, which is what L1, that is lasso regression, can do, versus L2 ridge regression. You should notice, however, that in that case, the alpha value of 100 is all the way at one end of this list of alpha values. What you could start to experiment with is just choose L1 as, or L1 ratio as 1, and then start experimenting with larger and larger alpha values, which are essentially just correlating back to some sort of lambda for lasso regression. Or maybe this is enough of a signal to not even bother using ElasticNet and just go straight to lasso, since you're basically performing that anyways. Okay, let's evaluate the model's performance. We'll say our y predictions is equal to grid model dot predict on scaled x test, and we'll say from sklearn dot metrics import mean absolute error, and let's check out the mean squared error as well. So we run this, and then we say mean absolute error comparing the y test to y predictions. Run that, and you can see that I'm pretty much getting the exact same results as expected because I used the exact same train test split. And then for the mean squared error or root mean squared error, what I would do is say NP SQRT on the mean squared error, again passing in y test and y predictions. Run that, and you pretty much get back something very similar. Now, it's not going to be possibly exact depending on what you followed along here, but it should be fairly darn close to something like this. You should only be off by at most a couple $100 on either of these. And hopefully you were able to maybe even improve on this performance depending on what parameters you provided to the model. Okay, so the question arises, is this an actual good prediction for this set of y-test variables? We don't know that without actually knowing the average sale price of a house. So let's check out the mean price of DF sale price. There we go. So it looks like the average house in our data set is about $180,000. And our predictions are off, typically, this mean absolute error, by around $14,000 with a root mean squared error, or kind of standard deviation here, of $20,000. I don't think that's too bad considering that you're kind of plus or minus 10%. The real question that arises here are, was it worth it to kind of do all of that work with the data set to get so many features? And what I would recommend doing is, since we're already going to an L1 ratio of 1, is to explore lasso regression and explore those coefficients that you can then grab directly and see what are the most important features there and kind of simplify your data set further. It's possible that you would worsen your MAE or root mean squared error, but I would say even if you worsen your MAE by up to like $1,000, but you're able to reduce 90% of those features we created, it's definitely worth the kind of trade-off there. Obviously, it depends on what you're really trying to achieve and how much computation you're willing to use for maintaining that large of a feature set. Okay, definitely explore this further, and I will see you in the next section.